Okay, I think it's good. Thank you very much for invitation. I think you will going to take a break from amplitudes for most of this talk. So this is gravitational instantons, old and new, and the new part, some of the new part will appear at the very end, and this will be based on joint work with Paul Todd. All right, so what are gravitational instantons? Well, they not really a mathematical definition, but roughly speaking, solutions to four-dimensional Einstein equations. And although I'll talk about Ricci-flat solutions, you could also talk about Einstein-Maxwell or cosmological Einstein equations, which are non-compact but complete Riemannian manifolds. So they're solutions in Euclidean signature, and they should asymptotically look like flat space. So to turn this into a mathematical definition, we would need to agree what it means to look like flat space asymptotically, and there are different ways in which this could happen. And this is an advertisement of a second edition of my book, which came out just 2 months ago, and you can read in the physics language some of it in this book. But I'll talk about a particular class of this gravitational instantons. So the way they approach a flat space will hopefully be clearly defined. Okay, so let's. It's always best to start with an example, and I'll tell you about the Euclidean Schwarzschild metric. So let's first look at the Schwarzschild solution, which describes the static black hole in Lorentzian signature in some coordinates, and these coordinates do not claim to cover the whole of space-time, but as things stand, so m here is a constant non-negative parameter, and r, theta, and phi are spherical coordinates on R3, and p is just a time coordinate. So there are two problems with this formula. The first one is when r equals 2m, the term which multiplies the r squared blows up. Now this, so physically this corresponds to the event horizon, and it looks like a singularity, but it's not really a singularity. You can remove that singularity by going to another sort of Eddington type cross-call coordinate system. Another problem is in the denominator of this 2m over r example. So when r equals 0, you clearly have a problem. And it's not now a coordinate artifact, which you can see by computing the norm of the Riemann tensor, and you will see that it blows up as some power of r when r goes to 0. Well, then you could be tempted to cure that problem by trying to remove the point or the region where r equals 0 from your space-time. So then you don't divide by 0. But if you do that, you'll find that there are geodesics in this metric which reach r equals 0 in finite time. So the space-time is incomplete. So one way or other, you do have a problem. Now the kind of surprise and a claim is that this problem disappears if you continue to Euclidean signature and you're willing to do something else. So first thing we'll do is we'll replace t by I tau. So tau is now real and p is therefore purely imaginary, and we restrict the range of r to be between 2m and infinity. Okay? So now, having made this restriction, you have gotten rid of a problem at r equals 0, but you have to worry about what happens when you approach r equals 2m. And you do that by Taylor expansion near r equals 2m, and with some experience, the way to, sometimes it flashes, sometimes it doesn't, but this is always best, right? So the way to do that is to introduce this coordinate rho, which is 0, where r equals 2m, and expand the metric near rho equals 0. So by change of coordinates at the level of this Euclidean Schwarzschild metric, you find that near rho equals 0, the metric looks like this. So this bit is a metric on a round two-sphere with radius given by 2m. And this bit looks familiar in that it should remind you of a way of writing a flat metric, but using plane polar coordinates, the kind of d rho squared plus rho squared d phi squared. So what plays the role of the angular coordinate here is tau. Now, so the way to make this regular, to make rho equals 0 regular, is to agree that tau is not on a real line, as it would be for the Schwarzschild metric, but it's a periodic coordinate, and it's periodic with this particular period. See, if you choose tau to be periodic with the period 8 pi m, then this bit is precisely a regular flat metric without conical singularities, but in plane polar coordinates. Okay, so that way we have convinced ourselves that this Euclidean Schwarzschild metric is in fact a regular, ever regular metric, and it's an example of a gravitational instanton. Whoops, oh, I didn't want to do that. Yeah, okay. You can do the same with the Kerr solution. The Kerr solution is more complicated. Depends on two parameters, mass and the angular momentum, and it's not static anymore, it's stationary. So if you just replace time by I tau, so make time imaginary, you're going to make the metric complex. What you have to do is to combine that with making the angular momentum imaginary, so what's called A in the Kerr solution, and that way you also construct with some periodicity identifications an instanton of Kerr instanton. So just going back to this Schwarzschild metric and this particular periodicity of the Euclidean time coordinate, which is 8 pi m, that kind of appears in Stephen Hawking's gravestone. You can, so there is this Hawking temperature, you can barely see, and it has lots of constants in it, but all these other constants like h bar c, gravitational constant k, think of them as one big one, and what's left then is 1 over 8 pi m. So that's in the first paper of Hawking, this Hawking temperature was not calculated using methods of Euclidean quantum gravity. He did that by computing the Bogoliubov transformation, but it was realized shortly after that work came out. It's realized by Gibbons and Perry that there is a simplified and very neat derivation of Hawking's temperature by identification between Euclidean quantum field theory and statistical mechanics, where this temperature is proportional to the inverse of the period we've just calculated. Okay, and that the formulae like that you can see for other instantons like Kerr. Okay, so this Euclidean Schwarzschild and Euclidean Kerr metrics are examples of a class of instantons known as asymptotically locally flat metrics. I'm going to define a metric to be ALF, or asymptotically locally flat, if it satisfies Einstein's equations with lambda equals 0 and asymptotically approaches a circle bundle over a two-sphere. Okay, and this, is if you like, in coordinates, such metrics in a limit where r goes to infinity would look like that. In the special case, if n equals 0, or equivalently, if this circle bundle over two-sphere is trivial, it's just a product of S2 times S1, you'll say that the metric is asymptotically flat. And both Euclidean Schwarzschild and Euclidean Kerr are examples of such asymptotically flat metrics or instantons. So asymptotically flat is some subset of asymptotically locally flat metrics. Now, in general relativity, in Lorentzian theory, there are black hole uniqueness results and of joint effort of David Robinson building on Carter and Hawking and Israel and others, which tell you that asymptotically flat spacetimes, black hole spacetimes where the singularities inside a horizon essentially have to belong to the Kerr family. So if they are static, they have to be Schwarzschild. If they stationary, they have to be Kerr. And this, these are theorems known as black hole uniqueness theorems. When this Euclidean quantum gravity was developed in late 70s, early 80s, it was natural to assume or search for a Riemannian version of this black hole uniqueness theorems. I mean, it became a conjecture, and the conjecture stated that Euclidean Schwarzschild and Euclidean Kerr solutions are the only asymptotically flat gravitational instantons. Okay, so how the history of this conjecture is quite interesting. So what if you want to have some support of this conjecture, what you would do is you would take the proofs of this Hawking-Carter-Israel-Robinson theorem and change T to IT, so to say, in these proofs and see if these proofs carry over. And what happens is the static version of this theorem, the one which leads to Schwarzschild, of Israel's theorem, that carries the proof is still valid in Riemannian signature. So it is a theorem, but a static asymptotically flat instanton has to be Euclidean Schwarzschild. The stationary version, which was presented by David Robinson and uses sigma model type identities, does not carry over to Riemannian signature. There are, I mean, technically speaking, there is a divergence. There is an identity which involves a divergence on one side and a sum of terms on the other side, where the next thing you do is divergence theorem and the fact that the terms on the other side of your identity are all positive to argue that they have to be zero. Now, in the Riemannian signature, these terms, some of the signs conspire against you, so that the argument doesn't work, but it was nevertheless believed that this conjecture, Riemannian black hole uniqueness conjecture, holds. Okay, but it turns out that it doesn't hold because there are counterexamples, or there is a family of counterexamples which were made explicit by Chen and Theo in a series of papers. And these are explicit examples, which I'm going to describe to you in a moment. So what they've done is they constructed a 5-parameter family of toric Ricci flat metric. Toric means that you have 2 commuting killing vectors. And these metrics depend on the parameters on the boundary on this parameter space. You have either a free center Gibbons-Hawking metric or Euclidean version of what's called Plebański-Demiański solution. And within this 5-parameter family of asymptotically flat metrics, there is a proper family of asymptotically flat instantons, and which I tell you what they are. So, but the price for disproving this conjecture is that these solutions are complicated. So here they go. It all builds on a quartic. So let's take f at the top of the slide to be a quartic with 4 real roots. Now, out of this quartic, you then construct even more complicated objects, call them f, h, and g, and from these objects you construct a metric. This didn't come out of the blue. They had a nice method of coming up with this metric. But as things are, this metric depends on 7 parameters because there are 5 coefficients of a quartic, and there is this parameter I'm calling nu, and there is another scale parameter I'm calling k. Okay, and then it's a matter of verification that for any values of these 7 parameters, this metric satisfies the vacuum-Einstein equations. there is some freedom in these parameters. So out of these 7 parameters, you can remove 2 by scalings, but that still leaves you a 5-parameter family of solutions. So now the next step is to do some global analysis and find the range of these coordinates x and y and the values of these parameters, which makes the matrix asymptotically flat. And the outcome is as follows. So let's, instead of thinking of the coefficients A0 up to A4, let's talk about the roots of this quartic, which I'm going to label R1, R2, R3, and R4. We assume that they're all real. And it turns out that if you order these roots, the range of the XY coordinates has to be in this rectangle here. The diagonal x equals y corresponds to infinity. So essentially, x has to be between R2 and R3, and y has to be between R1 and R2. And by doing that, you have cured all the curvature singularities in the metric. But what you end up with are these corners. I'll tell you more about those in a moment. And these corners will have conical singularities. But these conical singularities can be removed too by restricting the parameters. And when you do that, when the dust settles, you will find that you have a 2-parameter family of asymptotically flat instantons. The manifold which supports these instantons is CP2 with a circle removed. And here, Chen and Theo tell you how the roots of a quartic should depend on a parameter S in some range. So S is a 1 parameter in this family. The other parameter is what I called K on the slide below, the scale parameter. K is not that important, but S is. Okay, so here, if you go back to the previous slide where I gave you the formula for the metric, and you plug in the A's corresponding to these roots, you really have asymptotically flat instantons. Okay, now my purpose of this talk is to give a twisted description of these instantons, which brings self-dual Yang-Mills equations to it in an interesting way. So one feature of these Chen-Theo solutions is that they fall into a class of metrics with T2 action. So there are 2 commuting killing vectors, d by d phi 1, d by d phi 2. And any metric with such 2 commuting killing vectors can be put in the following form. So you have a matrix J, 2 by 2 symmetric matrix, depending on the coordinates Z and R. And the space of orbits of this T2 action is a disk with some corners. You can choose coordinates on it, which puts it in the isothermal form. So it's some function times the R squared plus the Z squared. So how do you construct these coordinates R and Z? So here's an algorithmic prescription which you can implement for any toric metric. First off, read off the matrix J. Well, that's easy. You just contract the metric with the 2 killing vectors. Then you compute the determinant of J, and you declare it to be R squared. That tells you what R is. Now, if this solution is Ricci flat, then R will automatically be a harmonic function, a solution of a Laplace equation on the orbit space. So it has a harmonic conjugate. We'll call that Z. So this Z is defined up to a flip of sign and an overall additive constant. And so you can do that for Schwarzschild, for Kerr solution, but also for Chen-Theo metrics. Now, I'll tell you about what's called the Rhodes structure. So you see, by construction of this coordinate R, the determinant of J is 0 when R equals 0. Well, that tells you that J as a matrix drops its rank. And generically, the rank of J is 2, but when it drops its rank, the rank will have to be 1 or it'll have to be 0. And generically, on the R equals 0 axis, the rank equals 1. and it's 0 only at the number of turning points, which are finite, where both killing vectors vanish, at the set of fixed points for the torus action. Okay, and that gives rise to what's called the rod structure. So here the axis which you see is the axis corresponding to r equals 0, the z-axis, and this axis is divided by rods. Each of these rods has is specified by a killing vector which vanishes on these rods, but then there'll be another one which doesn't vanish, except at these corner points. Some people call them nuts, but they're not quite nuts in the usual terminology, so I'm going to just call them turning points. So at these turning points, the rank of J equals 0. Turns out that if you do it for the Chen-Tio matrix, instantons, you'll have exactly 3 turning points. Okay, now what about this matrix J? Well, it's not arbitrary if G satisfies the vacuum Einstein equations. J turns out satisfies a single PDE known as the Young equation. So it's kind of a nonlinear version of a hyperbolic Laplacian. Now, it turns out that the same equation also arises as a reduction of anti-self-dual Young-Mills equations. And this is an observation of Witten Sr. and in a slightly different form of Richard Ward. So let's now, so what's my strategy? I'm going to see again this equation coming from anti-self-duality equations, and then I refer back to this Penrose-Ward correspondence, which Roland told us about, which parameterizes solutions to these equations by some holomorphic vector bundles. Now, concretely, you'll think of holomorphic vector bundles over a twistor space in terms of a patching matrix. And so my aim and the final product will be to produce this patching matrix for corresponding to J's, which correspond to Chen-Tio instantons. And I'll tell you what it is good for. Okay, so a crash course in anti-self-duality equations, my orientation choice is different to Roland's. And I'll be, rather than using this BF action, I'll use another formulation. I think as Atul said this morning, but there is no Lorentz invariant Lagrangian which produces anti-self-dual Young-Mills equations. Well, that's true, but there are actually Lagrangians where you don't need Lagrange multipliers as long as you prepare to make some gauge choices. So I'm going to make some such choices. Let's start off with complexified Minkowski space written in null coordinates, WZ, W tilde, and Z tilde, and pick a volume form. And let's take a Young-Mills potential to be a 1 form on this space with values in an SL2 algebra. Now, in these coordinates, anti-self-dual Young-Mills equations take this form. So the WZ, W tilde, Z tilde, and WW tilde minus ZZ tilde component of the Young-Mills field have to vanish. Now, so at this stage, we're going to make these gauge choices, and this is the kind of gauge which only exists because some of the equations hold. So you see, look at this equation first. Well, that tells you that there exists a case in which the W and the Z components of the potential are both 0. So the potential will have a bit of the W tilde and a bit of the Z tilde. Then you look at the second equation, and this, with a bit more work, this second equation is an integrability condition for existence of a matrix valued function, sort of, group valued function J, such that these two non-zero components of A are given, in terms of this J matrix acting like a potential. Okay? And finally, this equation has to hold, and this equation becomes a single nonlinear PDE for J, which is this equation. So the lesson from here is that as long as you prepared to make these gauge choices, which you always can, the anti-self-dual Yang-Mills equations reduce down to this single PDE. And although it's not important for my talk, this PDE actually does come from a concrete Lagrangian with no need for Lagrange multipliers. Now, what does it have to do with this Yang equation, which governs toric Ricci-flat metrics? Well, if you perform a symmetry reduction, so concretely, let's say that Z and Z tilde are given by these combinations of little t and little z, and W tilde is W bar, and you assume that J only depends on R and Z, that is it's a reduction by a translation and a rotation, then the anti-self-dual Yang-Mills equations by a calculation reduce down the Yang equation. Okay, so now the upshot of this is that you can now employ the twistor construction of solutions, generating solutions to the self-dual Yang-Mills equations to aim to solve the Yang equations, but that, as I've told you before, is equivalent to solving Ricci-flat condition with two commuting killing vectors. So how do you solve in these gauges, or how do you in principle solve anti-self-duality equations? Well, the underlying observation is that the anti-self-dual Yang-Mills condition is equivalent to the statement that the connection is flat on a certain family of two-dimensional planes in complexified Minkowski space, they're called alpha planes in Penrose's terminology. So here I'll be as concrete as I can. I write things down in coordinates. This formula I gives you these alpha planes explicitly. So if you fix alpha, beta, and lambda, indeed you have two linear equations on Minkowski space. It's a plane. But if you change alpha, beta, and lambda, it's a different plane. You can think of a space of all these self-dual planes, self-dual in the sense that their bivector is self-dual, and you declare this space to be the twistor space, and this twistor or projective twistor space, and this twistor space is CP free with a line removed. And the way I've set things up, alpha, beta, and lambda are affine coordinates on a patch in this twistor space. There needs another patch where lambda equals infinity. Now, so the twistor correspondence then translates between objects in this twistor space and in Minkowski space, and by definition, the points in the twistor space corresponds to alpha planes in Minkowski space. On the other hand, so what are the points in Minkowski space? Well, you look at this incidence relation again, and you fix WZ, W tilde, and Z tilde. So you fix a point in Minkowski space. What that gives you is a line, a copy of a CP1 in the twistor space. So points in Minkowski space are rational curves in PT, and the attraction or beauty of all this is that conformal structure, so Minkowski metric up to scale, can be encoded in algebraic geometry of these twistor lines. So you see, although these lines are complex and the twistor space is complex because everything is holomorphic, you can use three-dimensional intuition. The same way two lines generically miss each other in R3, two holomorphic lines miss each other in CP3. So you can, what does it mean for two lines to intersect? That's kind of a codimension one condition on the space of lines, and the calculation, which uses this incidence relation, will show you that two lines intersect corresponding to 2 points P1 and P2 if and only if P1 and P2 lie on an alcohol. Okay, and now the way this relates to anti-self-dual Young-Mills is this theorem of Ward, which expands on this anti-self-duality observation, which tells you that there is a one-to-one correspondence between equivalence classes of anti-self-dual Young-Mills potentials and holomorphic vector bundles over the twistor space, which are trivial on twistor lines. Now, how do you, so then the question is, and a really fair question is, to what extent is it an existence theorem, and to what extent it's a constructive way of finding solutions? So how would you go about implementing this in practice? Well, you'd cover a twistor space with two open sets, call one of them U, and on U lambda is not infinity, another one U tilde, where lambda is not zero. Well, with respect to this covering, a vector bundle like the one in Ward's theorem is represented by a patching matrix, P U U tilde, and because of our two-set covering, just one patching matrix is enough. And on the intersection of these two open sets, we can use alpha, beta, and lambda as coordinates. So it's a very concrete object, which tells you what the bundle is. So this is given to us because Ward tells us, let's start with a holomorphic vector bundle. Now, this bundle is trivial on twistor lines. What that means is that this patching matrix splits into something invertible and holomorphic on U, and something invertible and holomorphic on U tilde. And that it is this bit of a construction which is the hard part of the whole thing. So that's doing this splitting is a Riemann-Hilbert problem, and although it's algebraic, so you don't need to solve any differential equations there. In general, it's hardly possible to achieve, except for some special cases. Now, what's special about all this when you make these gauge choices, which correspond to the Young equation? Well, if you perform this splitting, so PU and PU tilde, you can then compute PU at lambda equals 0. You can do that because PU is holomorphic in a neighborhood containing 0. And you can compute PU tilde at lambda equals infinity. That gives you two matrices, H and H tilde. It then turns out, and this calculation is actually not hard at all, verifying that what I'm telling you here is true, that if you then take J, so two things happen. First of all, the connection is defined by these matrices H, and also its gauge equivalence to a connection which comes from a J matrix, and this J matrix is just obtained as a product of the H's. Okay, so if the lesson from here is once this splitting procedure has been performed, you can actually write down your J matrix. Okay, so now, so we're going to bring these two constructions together. When I say two constructions, one is relating Ricci flat metrics with two commuting killing vectors to the Young equation, and another one is realizing this Young equation as a self-duality equation. So how do you find the patching matrix starting from a Ricci flat metric with two killing vectors? Well, the prescription is this: you pick a killing vector which is non-zero on one of the rods which you're interested in, and you construct a twist potential for it. So a twist potential by definition is a function psi such that star k wedge dk is the psi. It's not always true for any killing vector on any four manifold that k wedge dk, when dualized, has to be a closed form, but for Ricci flat manifolds, it is true. So you find this psi, and then there's a bit of integrable systems technique. So in something called Backlund transformation, it turns out that if there is a J corresponding to your toric-Ricci flat metric, you can construct another J, I'm calling it J prime here, and you construct it out of this twist potential and out of a norm of the corresponding Killing vector. And this J prime also satisfies the same Young equation. But it is J prime which will be relevant for the twistor patching matrix, which then can be constructed as follows. You're going to pick a rod on which the Killing vector K is not identically 0. And then the patching matrix is given by an analytic continuation of this J prime evaluated at this rod, where you first you compute it as a function of Z, and then you replace Z by this combination. Now that's a kind of very low tech from the twister's perspective, way of doing it. There is a sophisticated, nice construction by Woodhouse and Mason, who take it a step further and say, okay, you've had to get the Young equation from self-dual Young-Mills equation. We reduce the self-dual Young-Mills equations by 2 symmetries. So rather than working on the whole twistor space, we might as well reduce the twistor space by these symmetries and work on some reduced version of it. But this reduced version is fairly pathological. It's a non-Hausdorff manifold, but if you're interested in how this would look like in this reduced context, you can read Lionel and Nick's paper. But I'm going to work directly on the twistor space. Okay, so what if you do all that, you read out this patching matrix and you analytically continue it, what sort of word bundle do you get? Well, it turns out that the patching matrix is rational. It's given by the components of this matrix are ratios of cubics and quadratics. So there are 3 monic cubics depending on the Chen-Theo parameters and one quadratic, which you can construct explicitly. If you do a calculation on the outer rod, which tends to where Z goes to infinity, you find that to the 0th order, the patching matrix is given by this, but up to the 1st order, it describes some asymptotic charges, in this case, the mass and the nut parameter. In the asymptotically flat case, this nut parameter is 0, and the mass you can compute, and this mass is given by this expression. It agrees by other masses computed by different methods by Kunduri and Lucchetti and others. You can also, so this, this patching matrix way of describing asymptotically flat or asymptotically locally flat gravitational instantons has an advantage of being able to provide you with the asymptotic charges. Just 2 minutes. Okay, so that's that's the end. So we'll talk about a particular class of gravitational instantons, this asymptotically flat class, and both asymptotically flat and asymptotically locally flat instantons would kind of be old, as in these were some of the first instantons constructed. What was new is the Chen-Theo instanton and its twistor description. Well, there is another, and I've defined for you asymptotically flat or locally flat by the behavior at infinity in terms of some circle vibration. The modern view on instanton does something else. What you do is you look at the volume growth of a geodesic ball of a large geodesic radius r, and then you argue that this volume of such a ball, the growth of this volume varies between linear and quartic, and depending on what it is, gives you a classification of instantons. So there are the ALE instantons, where this geodesic ball volume grows like r to the 4th. The ones I talked about, ALF, where there is a cubic growth, and you can really compute it taking something like Euclidean Schwarzschild, calculating its volume form and integrating over R. And this ALE and ALF are classical old type of instantons. You know, the instantons mentioned earlier today and yesterday, like Burns or Eguchi-Hansen, they are in these two classes. But there are two newer classes where the growth is quadratic. They called ALG by induction on letters, or R and R to the 4/3 ALH. And unlike ALE and ALF, these two other classes don't have, well, it's not known whether there are any explicit example of those. Now, with this asymptotically flat or locally flat instance, they a very hard open problem in the field is to, so we now know that this Euclidean black hole uniqueness doesn't hold, because apart from Kerr family, there is the Chen-Theo family of instantons. Question is, can there be any more? And it's not known if there can, but that's a problem. Less hard, but still hard, but maybe not very hard open problem is, are there any more toric asymptotically flat gravitational instantons? So this is the problem which one can and should be attacking using this Yang-Mills Yang equation type techniques and twistor techniques. But that is not known either. There is a recent theorem of Picard and Paul Godichon that the answer is no, that is Chen-Theo and Kerr are the only classes if you additionally assume that these instantons are Hermitian. But there is also a conjecture that they have to be Hermitian, but this conjecture hasn't been proven, and it'd be very nice if it was wrong. So a way to attack this problem, if you don't believe in the conjecture, if you believe there are more instantons, would be to look for solutions to these Yang equations where not 3, but 4 turning points, at least 4 turning points, so 5 rods. Okay, now what is, if anything, what does it have to do with amplitude? So I thought, but Roland tells me this was a stupid question to ask. I kind of thought that in amplitudes one really must have Lorentzian theory in mind, because if they know Lorentzian, if there is no time, then what scatters and where, right? So this is maybe too naive, but let's take it for now. So if you were to take this perspective, it would be natural to ask whether these Chen-Theo instantons have Lorentzian analogs. I mean, after all, Schwarzschild and Kerr instantons not only have Lorentzian analogs, but they came from these Lorentzian analogs in black holes. And if you look at the formula expression, it's not obvious that they have Lorentzian analogs or they don't have Lorentzian analogs. Maybe you need to change coordinates. But there is now an argument that these Chen-Theo instantons don't have Lorentzian analogs. And it's not as simple as saying that they don't because they self-dual, because they're not self-dual. They neither self-dual nor anti-self-dual, and nevertheless, they know continuations of any Lorentzian metrics. On the other hand, you can construct 2-2 analogs of these instantons. In fact, the kind of from experience, it seems to me that just about any complex solution to Einstein equations has a 2-2 version. Have a Lorentzian version is or Riemannian can be hard, but usually you can cook up a 2-2 version just by taking all the coordinates to be real. So that hasn't been done for Chen-Theo, but I think one could do that. So maybe these are relevant for for amplitudes, but that's where I stop.
Questions?
Yeah,
if I understood correctly, you said that there are no examples of ALH instantons with those scalings. Is that right? Or
of
the ALH examples? There are no.
What scalings?
With it, well, the R or the R to the 4/3. Is that true?
Okay, so there are no explicit examples of these instantons, but what is explicit, and it's explicit for this with this R to the 4/3.
That was what I was curious about. I was like, why would you guess that it would go like
these are called ALH star. You see, if you're familiar with the Gibbons-Hawking metric, you can take, so what's the simplest potential? What's the simplest solution to Gibbons-Hawking equations which are not flat? Well, they neither Taub-Nat nor Higuchi-Hansen, because what you can do is you can take the potential to be a linear function, but that satisfies the Laplace equation. So this gives you explicit metrics, and what is known is that this LAH star metrics asymptotically approach these Gibbons-Hawking metrics with linear potential, but only asymptotically.
Okay, thanks.
So I think the ALG case may have some relevance to these sort of amplitudes at strong coupling story, because I think the Aguri-Vafa metric is ALG, isn't it?
Yes. So well, again, yes, no, and yes in this order, right? So the Aguri-Vafa metric is not an instanton because it's not complete. So what's Aguri-Vafa is if you take a multi-Taub-Nat metric and you put all the centers, you put n centers on an axis, but then you take a limit where the number of centers goes to infinity, but the separation between the centers goes to 0. Then you can, it's a nice limit to take, but the metric you get is not, it's not a complete metric. And what's been shown is that asymptotically, these ALG metrics are approximated by Aguri-Vafa metrics. So, but I don't think it's fair to say that.
So I think GMN have this completion of this, and I think that's what forms the 8-particle amplitude at strong coupling.
Okay.
For the so that is in this twistor spaces for Y systems for amplitudes at strong coupling. I think that metric, which is deduced to exist on the back of the Aguri-Vafa one, I think that is so that's actually sort of gives you the amplitude as the Pabansky scalar for that metric.
So this is when you say for that metric, this is for Aguri-Vafa or for this?
For the one that makes an honest citizen out of it. So the Aguri-Vafa metric is as you say, it's an approximation to something which you can then make honest, and then there's then I think this is essentially Alde-Maldacena.
Right. So okay.
For 8 particles with restricted kinematics.
So is the statement that there is an explicit Plebansky scalar for ALG metrics?
Well, I mean, it's a complicated integral formula.
Okay.
But if you think that's explicit, then that's explicit.
Yeah, and so these ALG metrics, they not believed to possess any isometries. So as we both know, it is rare to have it's rare to have a Plebansky scalar in the case where there is no symmetry. Actually, no, that's not quite right. They can have S1 action. They can have S1 action.
Yeah, we'll only have,
but no more.
I think it has to have the S1 action because it's a Hitchin system.
Yeah. Okay.
I can't. Essentially, you're just looking at a 2-dimensional slice of this thing.
I see.
So, yeah. But sorry, but it's still sort of so Chen Tao is 3 nuts, and
yep.
2 nuts exhausted.
Well, two nuts is care.
Just a completely naive question, but okay, so Chen Tao is a counterexample to black hole uniqueness in Riemannian signature?
Yes.
If you solved your very hard problem and found that there was nothing beyond that in Riemannian signature, would you still have an open problem in 2-2 signature?
I think you would, and one of this, the starting point of this open problem would be to come up with the right definitions, what you really want from your gravitational instantons, and there, you know, lots of people have worked on it, and there are lots of examples. I mean, examples are easier to come by in total signature, but you know, with the right set of definitions, there will be an interesting theory. But you know, the experience is that the 2-2 signature is much less rigid. So all the kind of plane wave type solutions, which can be compact and don't exist in other signatures.
Okay, let's thank Maciej again.